Welcome to another podcast. In this episode, we're going to be taking a look at bifurcation diagrams in Maple. And I just want to kind of walk you through the process of creating a bifurcation diagram, what to look for, as well as give us a little bit more insight into autonomous equations. So I want to start off by loading the packages that we're going to need for this, and that is the plots package and of course, the DE tools package. Let's go ahead and load both of those. All right, the next thing I want to do is bring in the right-hand side of my differential equation. So these are autonomous equations that we're looking at, and so what I want to do is bring in the equation y squared minus u minus 2y. Now, that's the right-hand side of the equation, so I'm thinking of y prime equals this quantity. But I want to go ahead and call it f for now, and that way we can use it later down the road. All right, so let's see. I'm just going to refer to this as model, and I'm going to the model that I'm looking at for this problem is the differential equation y of t, comma t, so that's how you put y prime in there, equals, and I'm going to substitute in the value y equals y of t from f. So what this will do when I'm finished is we actually now have a differential equation. So basically all it did was it took y prime of t equal to, and it set in f, it set all the y's equal to y of t's, which is what we need. Now I want to make sure that you understand here that the u that we're working with here is a parameter. So it's not a variable. What it means is we decide the value of u before each and every problem. U could represent something like a harvesting constant in this case, because you're taking, so you're subtracting out u if u is positive. You're taking things away from a population, or if it was positive, it could be sort of some sort of restocking parameter where you're adding things back into the population. There's lots of reasons why you want to study parameters in differential equations, and this is just a small peek at that. Okay, the next thing I want to do is set up a sequence of parameters here, and so this is a sort of new thing for a lot of you. So I'm going to call this PARM for parameters, and I'm going to set this equal to a sequence of values. The sequence of values, let's see here, I want to do I over 2, where I goes from minus 10 to 10, and close it. So understand what this command is going to do is it's going to create a sequence starting at minus 5 all the way to positive 5, counting by halves. And so if I go ahead and hit enter here, it'll show you there are all the different values. And you can imagine that what I'm going to do with this is I'm going to set the value of u equal to each and every one of these parameters and sort of investigate what the solutions do for each parameter in this case. This is called a parameter study. Since this is a differential equation, we also need some initial conditions. And so I'm going to go ahead and create an initial condition group. And initial conditions, at least when you enter them in Maple, need to be in curly braces. So I'm going to start this off with curly braces. We're going to do another sequence here, and it's going to be a sequence of points. So we're going to let our solutions go through the point 0, I, where I is negative 4 to 4. All right. So there's my sequence. Those are all my different initial conditions for this problem. I'm going to have the graph go through negative 4, negative 3, negative 2, negative 1, and so on. All right, next up is I actually want to show you the phase portrait here. Okay, so remember the phase portrait is the graph of f, essentially, for this problem. So we're going to graph f, and let's just... we want to look at it for all these different parameter values. So I'm going to need to do an animation, and I'll show you how to do that. Let's just do it this way. I'm going to display a sequence of plots, and the sequence of plots depends on the value of u. So I'm going to plot the function f. My y values are going to range from minus 5 to 5. Let's make it a little bit thicker so it'll show up well on here. I'm going to change the color to blue, and I'm going to use a lot of points to do this. And then finally, I want to set it within my sequence here. This is what's iterating the sequence. I'm going to create a new sequence for each value of u in that parameter set that I have above. So we're going to create a total of 11 different plots here all at once. And what we want to do is draw them out in sequence. So this is what animates it, this command. So the command here is I've just created a bunch of plots. We're going to display all of them, and we're going to do them in sequence. That's going to create the animation. And then if I want to set up a viewing window, the best viewing window here is to go -5 to 5 and -10 to 10, I think, for this set should work out well. All right, let's see what it does. Okay, so here it's starting me off, and this first graph that it's showing me is the graph that corresponds to the first value of u in the parameter, which would be -5. So if u is -5, this is the graph in the phase plane. Notice there are no critical points. There are no critical points because this parabola does not cross the x-axis the y-axis anywhere. So remember, this is the y-axis versus y prime if we're looking at a bifurcation diagram. So I'm going to move this forward a little bit. So there's -4.5, -4, -3.5, -3, -2.5, -2, -1.5, -1. And look at -1, it touches. So when the parameter is -1, the phase portrait touches the y-axis for the first time. That's going to be important. As we keep going, now all of a sudden we have 2 critical points. We keep going from there, we have 2 critical points, and the critical points are spreading further apart as we look at the rest of our parameters. So that gives us a glimpse at what the phase portrait for this autonomous ODE with the parameter u is doing. All right, if we want to take this a little bit further, I want to go ahead and create another sequence, but this time I want to create a sequence of plots based off the actual solution of the differential equation. So it's going to be the display command again, because that's how you show multiple plots. And I'm actually going to display a sequence of DE plots rather than real plots, the plots of the phase portion. I'm actually going to do the plot of the differential equation. And so if you recall the differential equation we named model, and we're going to have it plot it for y of t being the solution, and our parameter t I'm going to range from 0 to 5. The y values from -10 to 10. And I want it to solve for each and every initial condition. So I'm going to show a bunch of solutions here, and those solutions are for the IC set, the initial condition set in our problem. All right, we're going to set the color of the slope field to black and the color of our solutions to blue. It looks best if you box the axis for this, and then I'm going to actually decrease the points a little bit so it renders a little bit more quickly. All right, so that is this command right here is how you would plot a slope field where you show all the solutions for each initial condition. Now I'm doing a sequence, and the sequence is based off of each particular value of u assumed in the parameter set that we defined earlier. And then once again, the way we iterate it is by doing in sequence equals true. All right. I should have called it num points instead of num points, so small error there. All right, let's let that render. All right, so I just want to bring this back to what we had going on up here. So we started off with this, and notice there are no critical points. Let's iterate each one of these one step forward. Just one step forward. One step forward here, one step forward here, still no critical points. Okay, let's move this forward to where we get our first critical point. Okay, that's on frame 9. Let's move it forward here to where we get our first critical point, frame 9. Notice there's now a horizontal solution at the value 1, because we said that when this was 1, that's when we get our critical point. Okay, So keep going. We're now at 2 critical points. You see how we have 2 horizontal lines? If we go back to this one, we're at 2 critical points there as well. So frame 10 to frame 11, we went from 0 critical points to 1 critical point to 2 critical points. Notice that changing the value of the parameter changed the nature of solutions, and as we keep going here, the critical points or the horizontal lines get further and further apart. So you can see here, this is an unstable critical point right here, and this is a stable critical point right here. Okay, let's go just a little bit further with it. And now we want to talk bifurcations, because anytime you have this sort of behavior where you go from where you change the number of critical points you have based on the parameter, then the parameter has what's called a bifurcation point. And we want to study those points because we want to know what are the special values of the parameters that change the nature of our solutions. So in order to do that, let's just recall for our sake here what f is. So f is the right-hand side of the differential equation, and what we basically want to do are find the critical points of f. So I'm going to set f equal to 0, and then I'm going to solve this equation. It's equation 6. I'm going to solve that equation for y. So we end up with 2 critical points here, one depending on what u is. And what you can see right away is that if u is -1, we get the point 1 repeated. So the bifurcation point here is u equal to -1. So we get a bifurcation at u equal to -1 because y equal to 1 has a multiple critical point of multiplicity 2 at that point. So that's how you determine bifurcation points. You look at the critical points based on the parameter u, and if there is a value of u that's critical, in this case -1 is critical, then that sort of is the bifurcation point that you're looking for. So the point is, you always do these based off of u and -1. So the bifurcation point is the uy equals -1, 1. That's where a bifurcation point occurs. Now, if you're wanting to view bifurcation points in a graph, then in the graph, you would need to have a different sort of graph than what we've done so far. Notice the graphs so far have been t versus y and y versus y prime, the phase portrait and the actual solution plot. If I want to look at the bifurcation point, then I need to look at what's called a bifurcation diagram. Bifurcation diagram plots u versus y. So it's a different sort of animal than what you are used to, and it's not the sort of thing that's easy to plot in your head. So using Maple is about the only good way of going about doing this for most of these problems. So here's how we're going to do it. This is why we loaded the plots package. We need the plots package to do display. We also need the plots package to do what's called implicit plot. So I'm going to do an implicit plot of the function f equal to 0. This is why it has to be implicit, because we're plotting the actual equation here. And I'm going to let my parameter be the x-axis, and I'm going to let it range from -4 to 4. And then the y values are going to be the vertical axis, also from -4 to 4. And I like to do these with point plots. So I'm going to say style is equal to point, and I want, let's see here, I want to view this. Actually, let me talk about the. Let me go ahead and do the view, and then I'll talk about how to change the number of points here. So there's the view. I'm going to let everything go from -2 to 4 and from -4 to 4. And then the color of this, let's just make that blue. And I did not spell plot correctly. So implicit plot. So you can see here how each one of these are points. They are points in the equation where I choose a u value and I look at the corresponding y value for that particular point. Meaning, basically, I plug each value of u into this, and sometimes I get two values, sometimes I get one value, and then over here, past -1, if I let u, the parameter, be less than -1, I get no y values to show up, which makes sense, right? There are no zeros if u is less than -1 because you get a negative underneath the square root, so you get no real solutions in that case. Now, sometimes you need to up the number of points. So I'm going to up it to, let's say, 5,000 here. Maybe we can see, let's go even higher, 50,000. So there's a nice solid line. And what you look for in a bifurcation diagram is where any turns are made. I know that's sort of that's sort of a simple concept, but notice the graph turns. And where does it turn? It turns at the point u equal to -1, y equal to 1, and as we said before, that's the bifurcation point. So the bifurcation point is going to occur where the graph turns in the equation, because if I think of a vertical line passing through this, over here the vertical line will not touch, which means there's no critical points. If it passes perfectly at the end of this one, there will be one critical point, and everywhere else it passes, I'm thinking of the phase line here when I say the vertical line. The phase line for any of these other points would have two critical points that are getting spaced further and further apart. And so this is how you think of a bifurcation diagram. The implicit plot command is how you're going to plot them. You're basically going to plot the right-hand side of the equation set equal to 0 and let u be the horizontal axis. So you've got, when you do this, you've got the parameter and you've got y. So we're going to let y be the vertical, u is going to be the horizontal in that case. All right, this is just sort of a glimpse at the concept of bifurcation diagrams and how that impacts critical points for autonomous differential equations. I encourage you to look through some of the Maple files that I've uploaded online and take a look at this. It'll help you with your next Maple lab that you're going to be doing. This will be Maple lab number 2. And so take a look at this. If you have any questions, come by and see me. But this is bifurcation diagrams in Maple. Thank you for watching.